Good day, dear listeners. My name is Aleksandr Voronka. I am student from Immanuel Kant Baltic Federal University and I am a member of Laboratory Mitochondrial Club. Here I will tell you in more detail about the work analysis of the mutation spectrum and selective constraints of SARS-CoV-2. As we all know, the SARS-CoV-2 pandemic is a big problem, both from the medical point of view and from the economic point of view. A more detailed analysis of the virus, understanding its evaluation trends, can help us in the fight against it. A signal of coronaviruses is a large genome. SARS-CoV-2 is not exception. He has about 30 kilobases. However, the difference between pairs and child are only about 610 nucleotides. The virus shows a large asymmetry in the mutation spectrum. A higher proportion of your mutations in uracil suggests, firstly, that the mutations are not random, and secondly, that the genome changed over time. To analyze this, we studied the changes in the virus genome during the year of the pandemic from December 2019 at three levels: nucleotides, codons, and amino acids. Let's start. At the beginning, we reconstructed the SARS-CoV-2 mutation spectrum using the two databases, Nexttrain and GSAID, to test ourselves. They are based on synonymous mutations because they are less affected by selection and mutagenesis is better visible. How was considered the proportion of each mutation? The number of mutations was divided by the number of synonymous nucleotides in the genome. It is the third nucleotide in the codon, from which the mutation occurred. Then the resulting number was divided by the sum of other mutations, and the proportion of mutations in the genome was obtained. The specters are similar. In both cases, mutations from cytosine and guanine to uracil predominate. All further calculations are based on data from GSAID. To check the change in the genome of the time, we took hundreds sequences from the beginning of the pandemic and the 100 last sequences from the full set at the time of writing this work. At the beginning, we calculated the content of nucleotides in the sequences. The table shows the average values for 100 sequences with confidence intervals. Where the confidence intervals do not intersect, we consider the changes significant. Okay, from top to bottom, and from all nucleotides to four-fold nucleotides, this is from the less natural position to the most natural position, and it means that the four-fold nucleotides can mutate into any nucleotide without changing the structure of the protein, which means that they are less affected by selection. We see that uracil increases significantly at all three levels. The proportion of other nucleotides decreases, although not always significantly. In addition, looking at the proportion of uracil at the beginning of pandemic, we see that it is already more than 50% in four-fold position. This may mean that the genome has already mutated according to similar laws before infecting the human population. We will continue our work on this issue. Okay, let's move on the synonymous mutations. To begin with, we calculated the codon usage among amino acids for the reference genome on the Wuhan isolate. Instead of thymine in the framework of RNA, it is uracil. Okay, now, for example, let's take the amino acid proline, for example. The sum of all 4 fractions that encode it is 1. For comfortable analysis, the amino acids that encode codons that differ not only in the third nucleotide are divided among themselves and are designated as the amino acid with first 2 nucleotides, like lysine, which starts with Cu, and lysine, which starts with 2 uracils. It can be seen that the proportion of codons with uracil at the end is higher than that of others. Next, let's look at the change during the year of the pandemic. We also calculated the average codon fraction for the initial and final sequences and subtracted the initial ones from the latter and ordered to trace the changes. The proportion of codons with uracil at the end are increasing. Also not everywhere, but which is statistically significant. We used the G criterion for verification. For example, let's take tryptophan. The proportion of the ACU codon increases, and with cytosine and guanine at the end decreases. Let's move on non-synonymous substitutions. We have built a table of the genetic code with the expected direction of mutations along the synonymous mutation spectrum. Thus, the amino acids were divided into losers. Mutation occur from them. Their shares should decrease. Intermediate gainers, mutation occur in and out of them. Their shares should be not change much. And gainers, mutations occur only in them. Their shares should increase. We consider the reference genome. Here are the fractions of each amino acid in the genome. We cannot say that we see the same butterfly as in the last picture. However, if we look at the change at the time, we will see that some amino acids behave as predicted. The proportions of proline and alanine decreases. Serine, lysine, valine remain unchanged. Phenylalanine, lysine increase. So we see half of the butterfly. Nevertheless, the change by the mutation spectrum are statistically significant. We verified it using the Spearman correlation. 2 vectors were compiled. The first contains of -1, 0, and 1 for losers, intermediate gainers, and gainers. The second consists changes in proportions. Okay, that is correlate. However, we still cannot say exactly which amino acids the mutation occurred from. To do this, we calculated the speed of mutations of amino acids for the year of the pandemic. The graph shows the speed. Dark bars shows speed along the mutation spectrum. The light ones are against it. Opposite speeds stay near from the amino acid A to B and from B to A. They are near. Okay. The arrows indicate the speed that statistically differ from each other. Green, the speed by the mutation spectrum is higher, and red, the opposite speed is higher. The 19 speeds differ statistically. The 11 is higher in the expected direction. Okay, how we made the calculations? A table was formed with the values of the number of mutations along the mutation spectrum and in the opposite direction. Also, the number of amino acids from the mutation occurred and into the mutation occurred. This 2x2 matrix was loaded and analyzed using Fisher test. If p-value is less than 0.05, then the changes are statistically significant. If the odds ratio is higher than 1, then the speed is higher along the mutation spectrum. The speed was calculated by dividing the number of mutations by the number of amino acids from which the mutation occurred. Okay. Further, all nucleotides were divided into conservative and non-conservative according to PhilOP data. The rates for conservative nucleotides are lower. 12 speeds differ, and 8 are higher in the direction by the mutation spectrum. The speed of non-conservative nucleotides is higher. From 16 speeds, 8 are higher in the expected direction. The percentage of mutation spectrum speeds in conservative nucleotides is even little higher than in non-conservative ones. However, the speeds in non-conservative ones are much higher. Thus, we see that content of nucleotides and codon usage obey the rules of the mutation spectrum of the virus. In addition, we see that the virus has already mutated in a similar way before the outbreak of the pandemic. The proportions of nucleotides in neutral position are still far from dynamic equilibrium, and the proportion of uracil will increase. Non-cineamous changes are most sensitive to selection because they change the structure of the protein. Nevertheless, the proportion of amino acids also changed according to the rules of the mutation spectrum. Although the opposite changes are statistically significant. Thus, selection is visible. I want to express my gratitude to the scientific supervisor and colleagues who helped me. All the program code, as well as all the tables and graphs, are presented in my repository on GitHub. In addition, there is also additional information, 192 component mutation spectrum with neighbors, mutation spectra for each gene, analysis on the proportion of amino acids for structure proteins and proteins of the replicative apparatus, and so on. In addition, I invite you to visit the channel of our laboratory. There are entertaining videos on a scientific topic, for example, about heat shock proteins, evolutionary trends, and evolution trends in mitochondria, and much more what our laboratory, Mitochondrial Club, does. Thank you for your attention. Then take precautions, take care of yourselves.